All right, we're going to start now. Chapter 8. This is going to be in some way, you're going to have a little bit common concept from chapter 6. Okay? So we're going to deal about alkene. So you have the E and E over here, right? So before we had alkane. So you have this, you have alkane. So that's the one we already dealt with, right? So now you have E and E instead of A and E, right? Alkene. So we're gonna see some reactions at the end. So what type of reactions you're gonna expect? And then what's going to be the cause for the reaction? Of course, double bond is the one, right? And then at the beginning, we're going to start from the property, like physical properties of boiling temperature, melting temperature, densities, like that. And then we're going to see some conformations like before. So for alkane, you had eclipse, stagger. If you have substitution, you're going to have the anti for the most stable conformation, right? So here you're going to see like that, but not exactly conformations. You're going to have the cis trans definition for that. We're going to deal those things. Okay? So let's start from the properties. Now, since we know alkane already, you can think of this as similar to that. Right? So why it is similar? You don't have any dipole over here. If you don't have any other functional group, if you have just the alkene, you don't have any dipole. Right? You don't have any hydrogen bonding there because you don't have oxygen there, right? You don't have hydrogen and oxygen. So only force you're going to have is dispersion interactions like alkane. So that's the reason why you're going to see values very close to alkane. Okay? So you can see over here, as an example, hexane. So this is alkane, you have 6 carbons, 1, 2, 3, 4, 5, 6, right? And then you have the hexene. So you have the double bond on the one carbon, the first carbon. So 1, 2, 3, 4, 5, 6, right? So since you have the double bond there, you have E and E, right? Hexene. So you have the same number of carbons, but you have the different number of hydrogens, of course, since you have double bond there, right? So both have a dispersion interaction between the molecules. So they're going to have close melting temperature, boiling temperature, densities like that, right? It's not that far off. You can compare the values, 69, 63, right? So that's the properties. Right? The point to be remembered is the only interactions you have between the molecules is dispersion interaction. One point. Dispersion. Okay? So other thing going to be similar to alkane. If you have the no branch alkene, the linear chain, they're going to have the higher dispersion force. If you have any substitutions on the carbon, they're going to decrease the dispersion interaction because you're going to have less contact between the molecules. Okay? So this point going to be common for both alkane and alkene. Right? Alright, so now this is the graph you can see with the increase in the carbon number. So you have the carbon number, say 2 over here, that is, you have ethene or ethylene, right? You have the 2 carbon and then you have the double bond between that. So they're going to represent these values over here, right? and then 3, 4, 5, 6, 7, 8. You're going to increase the carbon number from there, say all the way to 20. So you have the 20 carbons there. So now if you compare with the larger carbon numbers, what do you see? The higher melting temperature, higher boiling temperature. Okay? So this is same for alkane. We have the same trend, right? So shorter chain gonna have the lower boiling temperature, melting temperature. If you make that longer, the temperature gonna increase, right? The same thing over here for alkane. So more number of carbons you have in the chain, preferably a linear chain without the branch. You're gonna have the higher boiling and melting temperature, right? Alright, so you can call molecular weight for that. So more carbon you have, more mass can be there. Same thing, right? So you can say number of carbon increase or increase in molecular weight. Same thing, no difference, right? Alright. So now the one thing that is different than the alkane is degree of unsaturation. Okay, so you're going to see this term again and again, even in OChem 2. So when you see the spectra of the molecule, like NMR, IR, mass, we're going to go in detail in each chapter for this. So the degree of unsaturation is the thing that's going to give the clue of what type of molecule is going to be there. Right? Or to decide whether you're going to have the double bond in the molecule between the atoms, or you have the ring or the cyclic compound, or it is the non-cyclic linear chain molecule. So this is going to help to distinguish between them. Okay? So let's define degree of unsaturation. So before I define that, let's see alkane. That we already know, right? So say you have 2 carbon atoms, ethylene, right? So how many hydrogen you have? 1, 2, 3, 4, 5, 6, right? So what is going to be the formula for that? So if it is alkane, so this is going to be the formula you're going to have, right? So let's say you have N equals 2 for this molecule, and then apply the formula, right? So you're going to have how many hydrogens? So hydrogen is going to be, for that, so carbon is going to be 2, you have hydrogen going to be, so 2N plus 2, that many hydrogen you're going to have there. So 2 times 2 plus 2 going to be 6, right? So you have 1, 2, 3, 4, 5, 6. So that's the alkane, right? So now the point over here, if you have like this, you have the 0 degree of unsaturation because this is saturated molecule. That means all 4 bonds on the carbon are attached to with hydrogen or any other atom you have. So degree of unsaturation is going to be 0. That means all bonds are hybridized. You don't have any pi bond or POP orbital over here. So the saturation indicates that for the each carbon you have, the orbitals are mixed to give sp3 hybridization, right? So you're going to have the 4 sp3, so this is going to be 1, this is going to be 2, 3, and then 4th is going to be between the carbon, right? You have the 4 sp3 hybridization, right? Now, the degree of unsaturation means all orbitals are not mixed. Now you're going to have something like hydrogen out from there. So what you're gonna have is now these two gonna make the bond with this. So we're gonna take one bond out there, and then I'm gonna make a bond like this. So now this is alkene. Okay? So you have two less hydrogen than the before molecule, right? So you have the double bond between the carbon. Okay, that's the alkene. So now what's gonna be the formula for that? So if you're gonna write the formula, then what do? You're gonna change that formula. So I'm gonna write with a different color. Okay? So you're gonna change that. That's for alkene. So you have two less hydrogen than before, right? So you're gonna indicate that. You're gonna have Cn, you're gonna have H2n plus 2, that was for alkane. So now you have two less hydrogen there. So what's gonna be the result? So that's gonna give CnH2n. So now for this, the number of hydrogen gonna be this one, Cn and H2n, which is different than alkane. Okay? So this decrease in the hydrogen is called unsaturation. So each carbon you have here does not have 4 atoms bonded. You have one atom over here, one over here, and the third going to be the carbon. So you don't have the 4th atom. Right? You have only 3 atoms bonded. One less than alkane. That's the unsaturation. Okay? So now, for the unsaturation, you're going to track as the bond. Okay? So for this molecule, ethane, so you have that formula. So to have the ethene double bond, you have this formula. Right? So you have the 2 difference over there. So now you have the unsaturation for alkene. So what is going to be the number for unsaturation? 1, 2, 3, 4, 5. Right? So you're going to take 1 degree of unsaturation. Why? One bond requires 2 atoms. So if you talk about one single bond, say hydrogen and hydrogen, so one sigma bond you have requires 2 atoms over there. So you have 2 hydrogen less. So 2 hydrogen atoms less means 1 bond less. That's why 1 degree of unsaturation. Okay? So sometimes if you have the cyclic compound like this, also you're going to have 2 hydrogen less than the linear chain molecule. Right? So you can connect the end carbon, say carbon number 1, right? 2, 3, 4, 5, 6. So you're going to connect 1 and 6. So let's say this is 1, this is 6. If you connect these 2 carbons, going to be cyclic, right? And then you're going to remove the hydrogen because 1 and 6 carbon cannot have more than 4 bond, right? So 2 hydrogen going to be out over there. So it also less than 2 hydrogen than the alkane. Whenever you have the cyclic compound, that's going to have 2 hydrogen less than the corresponding linear chain molecule. So 2 hydrogen less means 1 degree of unsaturation. Okay? So this also has 1 degree of unsaturation. So sometimes for that, we also call the index of hydrogen deficiency, IDH. Same thing. Degree of unsaturation or IHD, going to be something, right? Index of hydrogen deficiency. So alkene is going to have less hydrogen than alkane. So now you know what is unsaturation. Okay? So now, if you're confused like how to count those degree of unsaturation, you can use the formula. Okay, so this is the formula. So this formula is going to be valid for all unsaturated molecule. Doesn't matter it's going to have hydrogen only or non-hydrogen atoms like oxygen, nitrogen, halogen, right? So it doesn't matter what types you have there, you can calculate the degree of unsaturation using this formula, right? So let's do example. Let's do the same molecule we saw before, okay? So you're gonna see C double bond C, and then you're gonna have H2 over here, H2 over here, right? Ethylene, same molecule, this one, okay? Let's calculate the degree of unsaturation for this. So now this formula says the degree of unsaturation, so this is going to be equal to number of carbons. You're going to count the carbon in the molecule. So how many carbon? So you're going to have one, you're going to have two, right? So 2 carbons, I'm going to write 2 over here, and then minus number of hydrogens. I'm going to count 1, 2, 3, 4. I have 4 hydrogens, I'm going to write 4 over here, and then divided by 2 in the formula. So halogen, do you have chlorine, bromine, iodine here? No, right? So I'm going to skip that. I don't have that. Number of nitrogen, I don't have any. So oxygen, it doesn't affect any because it has 2 bonds on either side. So this is the only atom I have, carbon and hydrogen, right? So you're gonna have plus at the end over there. So now I'm gonna solve that. So 2 minus 2 plus 1. So gonna be 1, right? So it has 1 degree of unsaturation. So let's see another example. This one. Even we don't know the structure, how the atoms are bound. That's fine. As long as you know the molecular formula, you know how many atoms of what type is there in the molecule, you can calculate that, right? So let's apply for this one. So you have number of carbon, how many? 6. Minus hydrogen 12 over 2. Oxygen doesn't affect, plus 1 in the formula. So now you're going to have 6 minus 6 plus 1. It's going to have 1 degree of unsaturation. So we can calculate it, right? The other one, second molecule, same formula. You're going to have 8 carbon minus 14 over 2. And then you have the halogen here now. So minus 2 halogen over 2 plus 1. So now you're going to solve that. So what's going to be the degree of unsaturation? 7, 0. So 14 over 2, 7.
Minus the 1.
And then chlorine, how many chlorine you have? 2. And then 2, yeah. There's a typo over here. So 8 minus 7 plus 1. So 1 plus 1, 2, right? So 2 degree of unsaturation. Or you can see like 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 8 carbons over there. Put all the hydrogens over there. And then add 2 chlorine over there. And then see how many bonds are missing. You can count that way too. Right? So you can always double check it. So this one. So you're going to have the 12, 1 over 2, 11 over 2, nitrogen 1, so 1 over 2, and then oxygen, you're going to skip that, plus 1, so you can use the formula, right? So this formula is applicable for all the molecules. As long as you know what atom, how many atoms. If you know that, you can use the formula. Okay, good. So in your test, I'm gonna give you this formula, but for the final, you have to memorize it. Okay. All right. So now, molecular structure, orbital structure. So we're gonna start from the orbital, right? So now I think this is gonna be already covered. So probably I'm gonna skip quickly, right? So say for example, ethane, right? So you have 6 hydrogen and then 2 carbon. And then ethane, you're gonna have 2 hydrogen in it, in each carbon. And then you're gonna have the ethine. So YNE, you have 1 hydrogen each. So for these molecules, we already saw the structures, right? When you deal with the hybridization, you have the sp3 for that, sp2 for that, sp for this one, triple bond, right? So if it is sp3, you're going to have carbon, and then you're going to have the 4 hybrid orbitals in that, and then you're going to have the hydrogen combined to that, right? If it is sp2, which is the focus over here, alkene, so now you're going to have something like this, right? So you have the 2 hydrogen each, and then you have the pure p orbital. So this is pure p orbital, normally pg orbital, okay? And then the same for the other one, you have the pure p orbital over here, and they're gonna combine on this side, right? So this is sp2 hybridization. So for the first one, the p is not shown over here, you can draw if you like that. So this is the p orbital. So p orbital is like that, right? And then you're going to have the overlap of the p orbital on the side, so you're going to have the pi bond with that. So all are going to be sigma bond. You have sigma over here, sigma, sigma, and then you have 1 pi bond, right? Do you remember that? We already covered that, right? In hybridization. So now we're going to deal Y and E later in different chapter. So if you have the triple bond, I'm going to draw over here, so it's going to be a revision. So what do you have? You have the carbon, sp, so you're going to have 2 hybrid orbitals. So this is sp, this is sp, and then you're going to have 2 pure p orbitals in there, right? So you're going to have, so pg for example, and then you're going to have the py for example, right? So now you're going to have from this overlap, you're going to have 1 pi bond, and for the other, you're going to have the another pi bond, right? So this is going to give another pi bond. So you can have 2 pi bonds if you have YNE. Okay, if you have sp, 2 pi bond, sp2, 1 pi bond, sp3, no pi, or sigma, right? So this is just the revision. So now you know what bonding going to be for the alkene.
Professor,
Uh-huh.
why was it for that one it was an ethylene instead of just ethylene?
This is the common, so don't be confused with the common and IUPAC. Two different things, right? So ethylene is common. Ethene is IUPAC. Okay, so if you get confused, just like step 1 name. So ANE, ENE, YNE. So just stick with the IUPAC. So now one difference, if you compare with alkane, is that the rotation. So if you see the conformation of alkane, what are you going to have? So you're going to have the rotation along the bond, right? So sometimes these two hydrogens going to be in one plane, eclipse, we're going to call that. And then sometimes going to be farthest away, about 60 degrees apart, going to be staggered, right? So you have the free rotation along this single bond between the carbon. So you're going to have the different conformations, right? So now, do you think you're going to have the same scenario for alkene? No, right? So let's say you have the alkene. So now you have the double bond over here, so you cannot rotate along this double bond, right? So these two are tightly held by one sigma bond and the other pi bond. So you're going to have the rotation restricted. You cannot. You can, if you supply too much energy and you're going to break the pi bond, then you can, but it's not easy to do that. It requires a lot of energy. Right? So at normal condition, room temperature, you cannot rotate this. Okay? So that's what it means. So this is alkene. So you have the pi bond, and then you have the sigma, the line over there. So you cannot rotate that. If you force to rotate it, then you're going to break the overlap, and then you're going to have the pure p orbital. Let's say one orbital is in one direction, like that, and the other orbital is going to be in this orbital like that. So they're going to be 90 degrees of each other, right? So this is one direction, the other in other direction. So no overlap between them. That means no pi bond. You are breaking that. So that's not allowed. So this doesn't happen unless you're going to supply a lot of energy. Okay? So you don't have any rotation of the single bond with pi bond.
Professor,
Uh-huh.
so is this affected when the molecular orbitals are in their anti-bonding node compared to the typical bonding node?
This is different. So anti-bonding is going to be above this. So here is the thing. So let's say, so you ask questions, so I'm going to quickly explain that. So carbon, so you're going to have this, right? You're going to have this like that. So remember Gen Chem chapter 11? They are molecular orbital like that, right? So this line over here is the sum of energy of the atoms when not combined. Okay? So if it's not combined, of course, it's going to have higher energy. Okay? So anything below that is going to be bonded. Anything above that is going to be anti-bonding. Okay? So in all reaction, all properties, we're going to deal below the atomic energy. Right? So above that, it doesn't exist at normal condition. So this is kind of like a very short-lived, like a transition state, right? You can force to be there at a certain very short time. It doesn't have any meaning for the reaction. Okay? So all those anti, we didn't include over here.
Okay, that's fine.
Yeah.
Okay, thank you.
So now, naming. Okay? So again, naming, all the rules you had for alkane are going to be the same thing over here. So we didn't do like a different rule for different compound. The rule is going to be same for every compound. Okay? Of course, if you have the different functional groups, then you're going to have one or two extra step on that. But all those alkane things are going to be common for all. Right? So if I recall what you did there. So see the molecule and then see the structure of that. Okay? So you're gonna find out the parent chain, that is the continuous carbon labeling to have the longest possible chain. So figure out that. And then see the branch you have, how many branches you have. And then figure it out what branch is connected to which carbon. You can identify the carbon labeling for the branch, right? And then just like sum all in one sentence, that's the name, right? Same thing. You're gonna do the same thing over here, but you have one extra point to that. So the extra point is gonna be this one, right? So you did not have this in the previous chapter. Now you have this. So if I cut off that and then take only the green box over here, so you're gonna do exactly same as chapter 6, previous chapter. Right? The exact same. So now you are adding this circle to that, double bond to that. Okay? So what is the extra point on that? Is when you choose the parent, double bond must be the part of parent. You cannot take double bond as a branch. So this is the part of parent. So both the carbon you have for the parent chain must have the double bonded carbons. So both carbon must be included as the parent. That's the extra step. Right? If you remember that, then everything else is going to be same as before. Right? So let's see the example of this one. So now, when I choose the carbon, so I'm going to go the longest possible one. So if I go this way, all the way over here like that, that's going to be the longest one. Right? So if I count the carbon, so 1, 2, 3, 4, 5, 6, 7. So you don't have any other way that you're going to have the more than 7 carbon in the chain. This is the longest possible, right? And I have the extra step over here. 1 and 2 carbons are part of the parent chain I have over here. Remember that. Include double bonded carbons in the parent chain. Okay? As far as possible, number should be closer to the double bonded carbon. So I cannot start from the right side of the carbon because the double bonded carbon is going to have the higher labeling. I cannot do that. So double bonded carbon is going to have the lowest possible carbon labeling. Okay? So now once you know that, you do the same thing. So write the parent first. So how many carbon? 7, right? If you have just a single bond, you're gonna write heptane for that. Now you have the double bond, so what are you gonna do? You're gonna change A and E to E and E. So that's what you're gonna do. E and E, and then you have the hept. So heptane to heptene, right? Because it is alkene, right? And then the position of the double bond in the 1 carbon, that's why you write 1 in there. If it was on the 3rd carbon over here, you're going to write 3 over here. So 1 is the carbon labeling that you have the double bond. So heptene, okay? And then you're going to go to the branch as before. So how many branches you have? You have 2 branches, right? So 2 branches, one going to be this, other going to be this. So you have the methyl, you have the ethyl, right? So this is ethyl, and then this is methyl, right? So you remember the carbon labeling? So now the question is whether you're going to write the methyl first or the ethyl first. alphabetical, the same rule we had before. So ethyl is gonna come first. So that's why you're gonna write ethyl and then methyl. So you're gonna write the carbon labeling for them. So you have the 5 carbon for the ethyl, so 5 ethyl, and then the 4th carbon you have for the methyl, so 4 methyl. Right? So same as last rule, only one addition is chain, the parent chain must have double bonded carbon. And then when you number so that the double bonded carbon is going to be the lowest possible labeling number. So if you follow that, it's going to be easy, right? So now let's do this one, second one. So if I do this, that's going to be the longest possible chain. So that's the parent, right? So you have the 6, so hexane. You're going to change to ENE, hexene. So hexene is going to be alkene. And then which carbon you have the double bond? You have the 3rd carbon, so you're going to write 3. Or you're going to write these two, 3 hexene. So same thing, both going to be correct. You're going to write the 3 before hexene or X3 both are the same thing. You can do either way, whatever you would like. Okay? And then 3hexene is going to be for the parent. You have that. Now what is going to be the branch? You have methyl on the 2nd carbon. So 2 methyl and then 3hexene. Right? You can also write this way. 2 methyl 3 hexene. Same thing. The 3 or the double bonded carbon you can include before ENE or before the alkene. So either one will be right. Any confusion on that? So don't take this as a new one. So think you are like reviewing the alkane nomenclature. So whatever you have for the alkane nomenclature, just add double bonded carbon into that. That's it. Right? Good? Okay. So now, so you don't need to worry about over here, but if you have like too many functional groups, what is that? Probably in the next, you have the priority order. Yeah, that's the table over here. So if these are the functional groups you have, if you have more than one functional group, like alcohol, acid, carbonyl, if you have that, you're gonna follow the priority order this way. So carboxylic acid is gonna have the highest priority. If you have the CO and OH over there, so this carbon is gonna be number 1. That means, okay. So you're gonna follow this order. So when we go to different chapter, we're gonna revisit this table again and again and again. Okay. So this is the priority. And then the next thing gonna be, if you have the polyene, that means many double bonded carbon. Bonded carbons, right? So for one alkane, you're gonna have 2 carbon with a double bond, right? If you have 4 carbon, 6 carbon, or 8 carbon with a double bond. If you have that, what are you gonna do? You're gonna do di, tri, tetra, penta, like that. Right? So this is the one example. So this one. So you have 2 double bond. So this is 1 double bond. This is 1. Right? So you're gonna say diene as compared to just in the previous example, because you have 2 alkenes there, alkene double bonds. So now what do? You're gonna do the same thing. So you're gonna choose the parent chain like this. So both double bonds can be part of the parent. You cannot exclude the double bond. Right? So now you're gonna number that. So how are you gonna number it? So if I do 1, 2, 3, 4, 5, 6 like that. So that's gonna be the closer to all the branching you have. Then if I go from the right, from the left. Okay. So what is gonna be the parent? So hexadiene, right? So you're gonna write hex, and then you're gonna specify the 2 and 4 diene, or you're gonna say 2, 4 hexadiene. You can also write this way, something. So here you just add A if you have the poly. So this is written after hex or before in. Okay? So you're gonna write that. So this is the extra you're gonna add. So this is gonna be extra added. Right? Only when you have the poly in, more than one in. So if you have just one in, you don't add A. If you have more than one, you're gonna add A. Okay? So 2, 3, 4, 5, 6, doesn't matter how many you have, you're gonna add A in that. So that's why you're gonna have 2, 4, X, A, diene, right? And then for the branch, you do the same as before. You have the methyl, you have the fluoro, right? So you're gonna have the fluoro, and then you have 2-methyl, and then you're gonna have the hexadiene after that. So hexadiene is gonna be the parent, and then 4-fluoro and 2-methyl gonna be the branch on that. And one more thing, G, so don't worry about this one. We're gonna cover later in this chapter. So this is gonna be the like cis and trans. We're gonna cover that. So this is gonna be the name. Okay? So that's how you're gonna write it. Alright, so second, the same thing. So don't worry about R and Z over here. So accept that. Now you can name, right? So you're gonna do the longest possible chain. So now you're gonna go this way, that way, over here, right? So you don't do the methyl way. So if you do 1, 2, 3, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So 10 gonna be, if you have carbon 10, what is gonna be the alkane name? Decane. That's gonna be the name, right? Now, this is alkene. If you have one double bond, you're gonna write decene, right? So you're gonna change to A and A. If you have poly in, then what are you gonna do? So you're gonna write dec. You're gonna add A on that, since it is poly. And then, how many? You have di. So you're gonna have diene. Right? That's gonna be the parent. So of course we're gonna specify the position 1 and 7. So you're gonna have first carbon 1, 2, 3, 4, 5, 6, 7 carbon. So this carbon and this carbon. So you're gonna do 1, 7 decadiene. That's the parent. Or you can write the other way, deca, and then 1, 7, and then you're gonna have diene. So this is also the same thing. These two are the same thing. You can write either way. Both are correct. Right, so this is the parent. So now you go to the branch after that. So what is going to be the branch? You have methyl over here. So this is methyl. And then you have another methyl over here. So this is also methyl. So you have dimethyl, right? So what going to be the position? 1, 2, 3, 4, 5, 6, 7, right? So 4 and 7. So you're going to write 4, you're going to write 7, and then dimethyl, right? Yeah, no 7, 8. This is 4 and 8. So these are for the cis trans, so you're going to cover later. So just see this part over here. 4, 8, dimethyl, and then you have the decane diene, right? Decadiene. Confused? Good, right? So no matter what complicated molecule you have, follow the same rule. So choose the parent that has all the double bonded carbon in it. And then when you number the carbon, make the labeling lowest possible for the double bonded carbon. That's why you started from the right. Because you're going to have the double bond on the first carbon there, not on the left side. Okay? If you start left side, you're going to have 1, 2, 3. Third carbon is going to be the double bonded. From the right, you're going to have the first carbon going to be the double bonded. So wait from the right, not from the left. What about the cyclic? Yep. Mm-hmm.
I think it was the 4-8 dimethyl. On the 8, do we assume that that's a hash? Or no? I see like the wedge on the 4. So this is coming studios
7.
on the 4, the methyl on the 4.
Methyl on the 4. This is the method. Oh, this one. Oh, that's why like R and G from there.
Oh.
So you are not seeing the orientation right now, just the naming.
Oh.
So orientation I'm going to cover it. So we're going to go to cis trans and E, G conformations. Then that will be easier. Okay. All right. So now cyclo. So if I write just this as an example, so I'm going to write this molecule. So CH3. So how you going to name this? This red circle molecule. So whatever carbon you have in the ring, that's going to be parent. Okay. So how many carbons you have? 1, 2. So always start from the branching carbon. 1 carbon there. 1, 2, 3, 4, 5, 6. So I'm going to write hexane. That's the parent. And then see the branch on that. Methyl, right? If you have more than 1 methyl, you're going to write the position of the carbon in the ring. 1, it is obvious, it is carbon number 1. You don't need to write the labeling, okay? So methyl gonna be the branch, and then hexane. That's the name, right? You're gonna do the same thing over here. So now what you're gonna do is you're gonna number that like before. So now you have the double bond. So what is going to be the name for the parent? So you're going to change that to ENE, right? So here you're going to write the double bonded carbon. It's not the methyl, it's the carbon. So remember, you're going to have the lowest possible number for the double bonded carbon. We start from there. Double bonded carbon. So 1 methyl cyclohexene. That's the one you said, right? Before you had hexane, now hexene. That's how you're gonna name it. Same rule as cycloalkane. And one addition is double bond added there. E and E added there. Okay? So the other one, this one, You can do similarly, right? So this one. So you have the cyclopentane and then cycloheptane, and you're gonna have the bronze after that. So very similar to alkane. Good? Right? Alright, so let's do this. Review alkane again, the naming of alkane. Okay? If you have any question, I'm gonna answer this and then we're gonna continue after that. Okay? So make sure you know it. You're gonna come again and again. You're gonna come every chapter.